Hi everyone. In today's video, we are going to be deriving an expression for the steady state absorption flux of a gas A into a liquid film thickness delta, beyond which the concentration is approximately zero. Once absorbed in the liquid, A is consumed by a first order reaction with the reaction rate K. All right, so let's model this by drawing out a container. This container contains all liquid, and outside of it there is vapor. And there is some distance here, which is our liquid film thickness, which is modeled by delta. And also outside of this container, there is a concentration of species A, which is equal to 0. Now, like it says in the problem statement, there's a reaction rate modeled by the variable K. Now, this is a first order reaction. So knowing this, we can say that our reaction is equal to our reaction rate K multiplied by the concentration of species A. So now we want to solve for the absorption flux over this liquid film thickness. So that absorption flux is going to be the molar flux of species A, and it's going to be evaluated at some point. Now we're going to have to set some position points here. So we're going to have a position over here and a position over here. So we're going to say that the position to the left is at point Z is equal to 0, and the position on the right is at point Z is equal to delta after it has crossed this entire film thickness. So if we take the molar concentration of A evaluated at Z is equal to 0, Fick's law tells us that this is the negative diffusion coefficient of A through B multiplied by the derivative of the concentration with respect to position. So now let's look at this from a different perspective. So if we draw out this box here, and we say that this box contains the concentration of species A, there's going to be some molar flux that is flowing from left to right in and out of this box. And this is the molar flux of species A. And we know that this molar flux is flowing from high concentration to low concentration. So knowing that, that is why we have this negative symbol right here. Okay, so now we can create an equation that is based off of this expression right here. So that is going to be the derivative of the concentration of species A with respect to time is equal to the negative derivative of the molar flux of component A with respect to position plus our reaction rate, plus the actual reaction constant R. So we already evaluated what R is, so let's plug that in down here. So this is going to be the derivative of the concentration of species A with respect to time is equal to the negative derivative of the molar flux of A with respect to our position Z. And plugging in for R, this is going to be minus the reaction rate K multiplied by the concentration of A. So we have an expression right here for the molar flux of A. So if we take that and plug that in down here, we can find a new expression. But first, I do want to point out that our problem statement says that we are in steady state. So this term right here is going to go to 0. So if we plug that in, we're going to have 0 is equal to the negative derivative of the molar flux of A with respect to Z minus our reaction rate K multiplied by the concentration of A. we can now go ahead and plug in our expression for the molar flux of A and take the derivative of that. So if we do that, we're going to have that 0 is equal to the second derivative of the concentration of A with respect to Z minus K divided by the diffusion coefficient of A through B multiplied by C. And this concentration term, is what we are going to be solving for. So we want to solve for C, like I said, and we're going to need some sort of unit to help us do that. So this unit is going to be called M. And this M unit is going to be equal to the square root of our reaction rate K divided by the diffusion coefficient of A through B. So now we can plug that in. So this is going to be the second derivative of our concentration of A with respect to Z is equal to M squared multiplied by C. So now if we think back to differential equations, this actually looks like a differential equation that we might be familiar with. So if we want to solve for C using a differential equation, C is equal to some constant A multiplied by the hyperbolic sine of mz plus b, another constant, multiplied by the hyperbolic cosine of mz. And super quick, I'm just going to move this up here. So now, if you are unfamiliar with hyperbolic sines and cosines, the hyperbolic sine of x is equal to e to the x minus e to the negative x divided by 2. Similarly, the hyperbolic cosine of x is equal to e to the x plus e to the negative x divided by 2. So we plug that back into our equation. This is going to be c is equal to a, some constant, multiplied by the hyperbolic sine of mz. So this is going to be e to the mz minus e to the negative mz divided by 2 plus our constant b multiplied by e to the mz plus e to the negative mz divided by 2. And we need to set some boundary conditions. And we need to figure out what we are evaluating from. So our boundaries are going to be over this liquid film thickness up here, because we're wanting to find the absorption flux over this liquid film thickness. So our boundaries are going to be at z is equal to 0 and z is equal to delta. So we're going to have to solve when z is equal to 0 and when z is equal to delta. So let's first start off when z is equal to 0. So when z is equal to 0, c is equal to our constant A multiplied by, if we plug in 0 into these exponential terms, this is going to be 1 minus 1 divided by 2. And then this is plus our constant B multiplied by 1 plus 1 over 2. Now, if we solve this out, we can see that at z is equal to 0, C is equal to B. And this concentration term right here is at that interface. So this is going to be the concentration of A at that interface, and that is equal to B. So we've solved for one of our constants. So now we can solve for A. So to do that, we're going to have to solve when Z is equal to delta. So I'm going to plug that back in to our original equation up here. So this is C is equal to A multiplied by the hyperbolic sine of m delta plus B, which we just solved for, which is the concentration of A at our interface, multiplied by the hyperbolic cosine of m delta. So now if we want to solve for A here, this is saying that A is equal to the negative concentration at that interface multiplied by the hyperbolic cosine of m delta divided by the hyperbolic sine of m delta. So now we have both our A and B terms, so I'm going to go ahead and plug those back into our original equation up here. So this was C is equal to A, which we just said that A is equal to this negative concentration at our interface multiplied by the hyperbolic cosine of m delta. And then this is multiplied by our hyperbolic sine of mz. And this is divided by the hyperbolic sine of m delta. And then we're going to add b, which we said b is the concentration at our interface multiplied by the hyperbolic cosine of mz. And just to make this more simple, I'm going to also multiply by the hyperbolic sine of m delta. So we can simply just expand this division symbol over. So now we're left with this equation, which seems extremely long, but there's actually certain relationships between hyperbolic sines and cosines that we can use in order to simplify this. So if we use those relationships to simplify this long equation down, we can find that C is equal to the concentration at that interface multiplied by the hyperbolic sine of m multiplied by z minus delta divided by the hyperbolic sine of m delta. So now if we take this equation that we have for C and plug it into this derivative right here, we're going to find that the derivative of the concentration of A with respect to Z is equal to negative m times the concentration at our interface multiplied by the hyperbolic cosine of m delta divided by the hyperbolic sine of m delta. And we can take this and plug this back into our original equation. So we're going to have that the molar flux of component A is equal to the negative diffusion coefficient, which I'm just going to leave as negative D, multiplied by our derivative of our concentration with A with respect to position Z. So we said that this was this long equation. And this is our absorption flux of a gas A into a liquid film thickness delta. So this is exactly what we were solving for. So this is our molar flux at position z is equal to 0. This is our absorption flux that we were solving for. If you wanted to, you could go a step further. These negative terms will cancel out here, and you can also plug back in our unit expression for m, that was right here, and plug that back in for all of these m terms here. But regardless if you take that extra step or not, this is our absorption flux through the liquid film thickness.